Good afternoon. I'm Sean Potter from NASA's Office of Communications, and we're here today to tell you about NASA's first Earth science small satellite constellation, the Cyclone Global Navigation Satellite System, otherwise known as CYGNSS. Scheduled to launch December 12 from Cape Canaveral Air Force Station in Florida, CYGNSS will use a fleet of 8 microsatellites to look inside tropical storms and hurricanes in a way no mission has done before. To start things off today, I'd like to introduce Thomas Zurbuchen, Associate Administrator for NASA's Science Mission Directorate. Thomas?
I'm really excited to be here today and talk to you about this mission and especially about Earth science. Because see, NASA's work on Earth science is making a difference in people's life all around the world every day. Earth science helps save lives. It also helps grow companies and create an awareness of environmental challenges that affect our lives today and tomorrow. Today, you'll hear about a mission that does just that. CYGNSS is the first mission of its kind that will gather never-before-seen details on the formation and intensity of tropical cyclones and hurricanes globally. Clearly, it's a mission that is not only vital for public safety, but also one of 100 NASA missions in the agency's portfolio that inspire the nation and excite and encourage young people around the world to pursue careers in science and technology, engineering, and math. CYGNSS will do what existing satellite technology can't in terms of measuring surface wind speeds inside hurricanes and tropical cyclones to improve our ability to predict how these deadly storms develop and evolve. It's truly a mission that will be vital for our Earth right now, from today's response to natural disasters to tomorrow's air quality and much more. NASA is working for you 24/7. Thank you.
All right, thank you very much, Thomas. Now, before we introduce our panelists, I'd like to take just a moment here to go over a few brief housekeeping notes. If you're interested in finding out any information about this mission, you can do so by visiting our special mission website, which is found online at www.nasa.gov/CYGNSS, and that's spelled CYGNS, all lowercase. And if you're following us on social media and would like to ask a question for our panelists, you can do so using the hashtag AskNASA. And now I'd like to introduce our panelists of CYGNSS mission experts. Directly to my left is Christine Bonnickson, CYGNSS Program Executive here at NASA headquarters. To her left is John Shearer, CYGNSS Project Manager at the Southwest Research Institute in San Antonio. Next to John is Chris Ruff, CYGNSS Principal Investigator from the University of Michigan in Ann Arbor. And finally, we have Mary Morris, a PhD student in the Climate and Space Studies Department at the University of Michigan. So we'll start things off with Christine.
Thank you, Sean. This is a really good day for Earth science. Could you bring up my first slide, please? Earth science has worked for many, many years on looking at all the processes on the Earth. And as you see here, we've got a number of satellites that are up there trying to do that. But science and technology has progressed a great deal over the last few years. And there's a lot of new ideas on how to use that technology. And as part of that, next slide, please, we launched the Earth Venture Class program. Now, there are 3 strands to that. There's the suborbital, where we do investigations with aircraft, balloons, ground in situ measurements. We have instruments that we put on the Earth's, on ISS and onto other payloads. And we've also got full missions, of which CYGNSS is our flagship mission for this. This is where it includes launch, it includes building the satellites, it includes getting it into operations and operating it, in the case of CYGNSS, for 2 full years with a very minimal cost point. CYGNSS will be launched and operated for $162 million, including all the building and all the science. Like all space missions, CYGNSS has a portion that goes into space and a portion that stays here on the ground. Next slide, please. What you see behind me are the pieces of CYGNSS that go into space. On the left is the instrument. In the center, you see the fully assembled spacecraft. And if you want to know exactly how big that is, at the far end of the table here is a model of the full-size spacecraft that we're talking about. Then the big column you see at the end, this is the deployment module that will, when we launch, have 8 spacecraft locked onto this to get us into orbit. Next slide. The ground segment consists of 3 pieces. There's the communication stations where we get our data down and we control our satellites. There's the Mission Operations Center that's going to be in Boulder, Colorado, and then the Science Operations Center up at the University of Michigan. And you'll hear about all of these as we go through this presentation. What I want to leave you with is that Cygnus as a flagship mission, in addition to being low cost, came in on schedule, on cost, and on science. With that, I will turn it over to John Scheer, who will tell us how we got to this point.
Okay, thank you. Yes, I'm John Scheer. I'm the Cygnus project manager, and I'd like to tell you a little bit about the mission. First off, let's talk a little bit about the observatory. As Chris said, this is a full-size mock-up of the spacecraft over here. It weighs about 64 pounds, and it's basically, when the solar arrays are stowed, it's about the size of a carry-on suitcase. And to me, that's one of the neatest things about this. We're doing real science with a spacecraft that can literally sit on your desk right here. And not just one of them, but we'll have 8. They'll be orbiting in the tropics where the hurricanes are, and every 90 minutes they'll be making another measurement. Next slide, please. So each spacecraft has a payload called the Delay Doppler Mapping Instrument on board. It's basically a fancy GPS receiver that's capable of tracking 4 different GPS signals simultaneously. And then we have 2 large antennas that are facing downward, looking to the ocean, and then an upward-facing antenna also. The whole payload weighs 7 pounds and only takes 12 watts of power. Okay, next slide. So Chris will talk about how we use reflected GPS to measure the wind speed. But from an engineering standpoint, doing this is really an enabling technology for Cygnus. Because the Cygnus spacecraft don't have to generate the signal or transmit the signal, all they have to do is receive the signal. It takes very little power. The Cygnus spacecraft operate on about 60 watts of power, equivalent to a 60-watt light bulb in your house. And what that allows is a small spacecraft, small solar arrays, and allows us to launch 8 very small spacecraft on a single low-cost launch vehicle. Next slide. As Chris said, the 8 microsats get attached to the deployment module, which stays actually attached to the launch vehicle. Once the launch vehicle puts us in the correct orbit, altitude, and orientation, the launch vehicle will send a signal to the deployment module to release the 8 microsats. Next slide. So now I'm going to walk through some photos of the construction and test of the constellation and the flight segment. This is a picture early on of one of the 8 microsats under construction. You can see the structure internal to the microsat and one of the nadir-facing science antennas. Next slide. As we went through integration, each component was integrated to the microsat, and following each integration step, we performed a functional test to make sure that that particular component or subsystem worked correctly, and also to make sure that it played correctly with the microsat. So this picture actually shows a very good shot of the overall scale of a microsat. You have 2 other ones in the background there also. Next slide. We did solar array deployment tests many times throughout the integration test campaign. We did them at different temperatures, under vacuum, pre and post environmental tests. Next slide. One of the environmental tests that we did was called a thermal vacuum test. This is a shot of 4 different microsats going into the thermal vacuum chamber. The chamber was pumped down and basically simulated the vacuum environment of space. And then we would cycle the chamber to the different predicted extreme temperatures that we'll see in space. Again, just to make sure that when we get on orbit, everything works correctly. Next slide. Because Cygnus is a sensitive RF receiver payload, one of the tests we did was what we call the plugs out test, where we took a microsat and put it in a RF anechoic chamber, which is an RF quiet room, and literally unplugged it from everything. So we were running the microsat over RF with the batteries, just like it is on orbit, and to make sure that the noise floor was low enough for us to make the sensitive measurements that we need for the science. Next slide. One of the final tests we did before delivery to Vandenberg was a flight segment vibration test. This is a shot showing the 8 microsats mounted to the deployment module on the adapter cone on a vibration table. We shook the flight segment to the predicted flight levels, and then following that test, we deployed each microsat from the deployment module to make sure that that still worked. We then did a functional test on each microsat, and then that included deployment of each solar array. Next slide. So this is what we call our cherry on top photograph. This was taken about a week ago out at Vandenberg. This is a picture of the flight segment with 8 microsats mounted on top of the Pegasus rocket. As of today, there's one side of the fairing on, and the second half of it is scheduled to go on next Monday. Next slide. So the Pegasus launch system is a little bit unique from a lot of rockets that I think most people are typical or used to. It's an air launch system. The rocket, which you see here in this picture, hangs off of a L-1011 airplane. The airplane takes the whole rocket up to about 40,000 feet, drops the payload, the rocket, and then 5 seconds later, the rocket engines ignite. Next slide. This is a picture showing the Pegasus mounted on the bottom side of the L-1011, ready for takeoff. Okay, next please. So now I've got a video, an artist rendition of the deployment sequence. Again, the launch vehicle is responsible for getting us into the correct altitude and orientation, and then we'll send a signal to the deployment module, and the microsats each have their own release mechanism and push-off springs. They release in opposing pairs, and each pair is released 30 seconds after the previous pair, and then 10 minutes later after separation, the solar arrays automatically deploy. The microsats automatically turn on once they're separated from the deployment module. And now Chris will talk about the Cygnus science that we're going to do.
Okay, thanks, John. Yeah, I'm Chris Ruff, the principal investigator on Cygnus. And as you've heard, Cygnus is designed to measure winds over the ocean, and it makes the measurements in 2 important different ways that are going to enable it to improve on our ability to monitor the inner core of hurricanes and ultimately improve our ability to forecast hurricanes. And I wanted to set the stage here first by doing a quick review of how we measure winds from space over the ocean today. And this first slide is an example of a typical technique that's used today. The satellite on the left is the NASA TRMM satellite, and one of the instruments on it is the TRMM Microwave Imager, TMI. It's the large white antenna on the top left in the picture of the satellite. And these are 2 data products that are generated by TMI. The top one is a measurement of the rain, or the rain rate, the precipitation everywhere in the tropics, and the bottom one is a measurement of the ocean wind speed. So this instrument can measure ocean wind. There's 2 important limitations in this type of measurement, which are common to all current techniques that can measure the wind over the ocean. The first one is the fact that wherever the rain is heavy in the top picture, if you look down at the same spot in the wind image, it's black. And the reason for that is that these signals that are used cannot penetrate through rain. The reason they can't is because of the wavelengths that are used. This is a system that operates at a 8 millimeter radio wavelength, and 8 millimeters is about the same size as a large raindrop, so there's too much interaction with the rain and you can't penetrate. So that's one limitation. We can't see through rain. The other limitation, as you can see in the title to these slides, these are 3-day images, and what that means is it took about 3 days of orbiting by this satellite before it covered the entire world once. So it takes 3 days to get an image of the Earth. And with the critical short timescale processes in a hurricane, especially the rapid intensification phase when a hurricane transitions from a tropical depression or storm to a hurricane, that typically happens on timescales of hours to maybe a full day. And if you only sample once every 3 days, you'll miss it. So the 2 critical things that we're trying to do with Cygnus are to sample much more often than once every 3 days and to be able to penetrate through the rain. The reason for that is that The primary limitation with our current ability to forecast how strong a hurricane is going to be in the future is our inability to see what's going on in the inner core of the hurricane. We can forecast where a hurricane is going to go fairly well because that's determined by environmental fields away from the hurricane, which are easy to measure now with existing satellites, but we can't measure what's happening in the center of the hurricane, which is what drives its rapid intensification. So we need to be able to penetrate through the rain, and we need to be able to measure more often. If we can go to the next slide, this is an example of the one way we have today of measuring the winds inside of a hurricane. And this is the primary standard that's used for classifying hurricanes today, whether it's a Cat 1, Cat 2, et cetera. It's an instrument called the SFMR, and it flies on the NOAA P-3 Hurricane Hunter airplanes. This is a picture of the instrument in the lower left, and then the installation on the under the wing of the airplane. These instruments operate at about a 5-centimeter microwave wavelength, and that's sufficient. That's about 10 times the size of a raindrop. So there's some interaction with the rain, but not enough to completely block the signal. So we can see both the rain and the surface below it, and these instruments can measure the wind in hurricanes. And if we go to the next slide, you'll see an example of measurements made by this instrument. This is Hurricane Katrina, about a day before it made landfall, and that black arrow through the hurricane in the picture is the flight line of the airplane, the flight line of the P-3, and then in the lower right are the measurements made as it was flying through the hurricane. And you can see that it's able to distinguish the peak wind right on the eye wall up about 65 meters per second, and it's also able to see the rain and retrieve the rain rate because of its wavelength. So this instrument in principle would give us what we need. The problem is you can't scale this type of measurement to space. It would take about a 20-meter antenna in order to make this measurement from space, and that's why these airplanes get down to about 2-3 kilometers altitude when they fly into the hurricane. So it's not practical. We actually could fly a 20-meter antenna, but we could never fly a large constellation of things that big, and a constellation of satellites is what's necessary in order to get the revisit time of the measurements down to the hour time scale. So we need to do two things with Cygnus to improve on what we have today. We need to be able to work at a long wavelength to get through the rain, and we need to make the instruments small enough so that we can afford a constellation of these to get the revisit time. And that leads me to the next slide, which sort of walks through the measurement principle that Cygnus uses. It's a completely different technique than the types of instruments that are on orbit today. As John was mentioning, it's a GPS bistatic radar, so the transmitter is the constellation of GPS satellites, and the receiver is our Cygnus observatories. And for each pair, a Cygnus receiver and a GPS transmitter, there's one unique spot on the ground where we can make our measurement called the specular point. And if the ocean were perfectly smooth, all of the reflection would originate from that one spot on the ground, and we'd be able to measure the wind right there. In this next picture here, you'll see an example of specular reflection. Specular reflection means perfect mirror reflection in electromagnetic ease. And this is an example of specular reflection at optical wavelengths where the moon you can see in the sky, and then the reflection of the moon in the lake is almost as sharp as the moon itself. And it's because the lake surface is so smooth that you get a nice mirror-like specular reflection. In the next image, you'll see what happens when the wind blows and the surface roughens. You get diffuse scattering instead of specular scattering, and it spreads out over a region called the glistening zone that surrounds the specular point. So if we could image this type of reflection at long microwave wavelengths, then we'd be able to back out the wind speed. And in this next image here, you'll see an example of that. This was a measurement made about 10 years ago by a technology demonstration satellite mission, which flew a prototype of the Cygnus payload on it. And it's a measurement of the diffuse scattering from the ocean surface. And you can see the specular point, that red hot spot near the top, and then the yellow horseshoe thing going away from it is the diffuse scattering due to the roughness. And this is the raw data that Cygnus measures, is these delay Doppler maps that show the diffuse scattering away from the specular point. And one last point I want to make here is that the GPS satellites were intentionally designed to work in heavy rain because like the navigation system in your car or your cell phone works just fine when it's raining hard, and it does that by operating at a very long wavelength, 19-centimeter wavelength, which is plenty long enough to be able to avoid scattering and absorption by the rain. So this signal is going to work just fine in heavy rain. Okay, the next slide. This is a video that gives you an idea of how the sampling works. So we've got 8 satellites in a single orbit plane, and here they are evenly spread out around the orbit plane. Each satellite has 2 antennas looking down at the Earth. Those are those red ovals to either side of the sub-satellite point. And then for each satellite, there'll be a series of specular points, and those are the blue ovals. And each specular point corresponds to one combination of a transmitter and a receiver. So the satellite is tracking these specular points, and as soon as they enter the antenna pattern, it acquires them and starts processing the diffuse scattering measurements, or the scattering cross-sections, and from those we get the wind. So each of these satellites has enough onboard processing power to do 4 of these measurements simultaneously. So it's as if each satellite was making the type of measurements that 4 different P-3 Hurricane Hunter airplanes were making. And then we have 8 of the satellites and 4 measurements each, so it's like having 32 virtual airplanes flying around somewhere in the tropics making measurements simultaneously. That's more or less what the data product will look like. And this is an illustration of what happens when you paste all of that together. You get all of these satellites flying in concert, making the measurements, and over time, they'll fill in more and more of the tropics as the Earth rotates underneath of the orbit plane. In the next video after this, it'll show you what the coverage looks like over the course of 24 hours. So this is the complete coverage by the full 8 satellite constellation over 24 hours and how well it fills in. The average revisit time at any spot in the tropics is about 7 hours. So we'll have a complete refresh of the tropical wind distribution, including under the heavy precip, every 7 hours. And the last slide just gives you an example of we have a detailed software simulator that predicts what we expect our measurements to look like. And the top left picture is a simulated hurricane, and then the black line is a track of the specular point as it passes through the eye, similar to the flight line of the P-3 airplane. And then the retrieval of the wind speed is shown in the lower right. The dark blue line is the idealized true wind that we fed into this simulator, and then the dashed line is our expected retrieved wind speed. And you can see that it picks out both the deep null in the eye of the hurricane and also the peak wind speed on the southeastern eye wall as it passes out of the hurricane. So what we're hoping is that these type of measurements will be absorbed into the National Hurricane Center data assimilation schemes, similar to the way they use their airplanes now, except that they'll be 24/7 for 2 years everywhere in the tropics. And with that, I'd like to hand the mic over to my grad student, Mary, who's working on ways that we can use this data to do some science.
Thanks, Chris. So now that we've heard a little bit about the science and the engineering aspects of Cygnus, I'm going to talk to you about one of the tools that we've been developing to address some of the applications of Cygnus. And this tool is called SIFT, or the Storm Intersection Forecast Tool. So we developed SIFT because we needed a way to predict ahead of time when and where Cygnus is going to intersect through storms and get really valuable hurricane data. And the other thing that we want to answer with this tool is, after we get that really valuable data, how soon after can we then downlink the data and get it to the users as soon as possible? So those are the 2 objectives of this tool. So today we're going to take a time machine and we're going to pretend that Cygnus launched a year ago. And we're going to do a little experiment to see what Cygnus would have seen if it had been orbiting during Hurricane Matthew a little over a month ago. So let's go to the animation and play it. So what you're seeing now is SIFT in sort of a global view mode. And each of these colored triangles represents one of the Cygnus satellites, and the dots that surround each satellite are the specular points that our orbit propagator can predict where they are. What I just turned on are all the ground zone contact zones that we can, whenever a satellite is orbiting over these circles, we can downlink the data to either our ground stations in Hawaii, Chile, or Australia. The other aspect of this tool is we can plot out where the ground tracks are. So what I just turned on is one ground track for just about an orbit for just one satellite. If you can imagine, if we add time and we turn on all 8 satellites, we're going to get great coverage over the tropics where we expect most of the tropical cyclones to be. The next thing that we want to answer with this tool is, where is all of our data? So the next thing that I'm going to be turning on here is the tracks of all the specular points. That's where our data is. That's where we're measuring ocean surface wind speed. So those are the 2 main aspects of this tool. The next thing that we want to address is, when are we going to intersect with Hurricane Matthew? So the next thing that we're going to turn on is Hurricane Matthew's position and size according to the National Hurricane Center's forecast at the initial time period of this tool. So the bright red circle on the screen is the current position and size of the storm. And we're using this tool to propagate the orbit in time to see where we're going to intersect the storm first. So as you can see now, Hurricane Matthew is tracking to the west, and then it's forecasted to eventually turn north, but we want to see when Cygnus is going to get close. We want to zoom in on the time and place that's first going to happen so we can see where our data is going to be. So right now we're getting pretty close, so we're going to zoom in and look at this further. So right now you're seeing a zoomed in view, and again, the bright red circle is where we're interested in currently. So what I'm about to do is I'm going to turn on all the specular point tracks over a couple of hours around this time period and put the satellites back in animation. You can see those orbiting to the bottom right of the screen. And right now we're starting to get really valuable data in that bright red circle. That's where we expect the highest wind speeds to be. And we can do really interesting stuff with this data. We can ask questions like, how intense is the hurricane right now? How far out do strong winds extend? Answering questions like how big is the storm? So that now that we know where the data is and when it's happening, and we want to look at all the data that we can get. So right now let's zoom out and look at all the data that we have collected over this time period. And you're going to see that we get a lot of great data near the environment of Hurricane Matthew. That's going to be really valuable. So the next question that we want to answer with this tool is, how soon after we get that data can we then downlink it to the ground? So let's go back to our ground zone contacts and put these satellites back in animation, and you're going to see that after we go over the region of Hurricane Matthew, our satellites then orbit directly over the Australian ground station, and we can get that data down to the ground within an hour. And that's a really great data latency, and it's one of the amazing aspects of Cygnus and using a constellation like this. So I'd just like to end by saying that this is just one of the many amazing projects that I've been able to work on as a student, as a part of the Cygnus mission, and I'm just really excited to see what we do next with Cygnus and see all the data come down shortly. Thanks. Back to you, Sean.
Great. Thank you, Mary. And before we start taking any questions, I'd just like to hand it back over to Christine Bonnickson for a few closing remarks.
Thank you, Sean. We've provided you a lot of data, but what I want to leave you with is that Cygnus is a tool that will provide us 24/7 coverage of the tropical cyclone zone, and it will improve our knowledge of how hurricanes grow so that we can better prepare and protect the people in the path of each hurricane as it comes. Sean?
Great. Thank you, Christine, and thank you to all of our panelists. All right, now we'll take some of your questions, and just a reminder, if you are following us on social media, you can ask questions for our panelists using the hashtag AskNASA. But I think we'll start with, see if we have any questions here in the room. We have one. Could you please identify yourself and your affiliation, please?
Yeah, I'm Matt Leonard with Government Computer News. One thing I want some clarification on is how the Cygnus satellite interacts with the satellites that are providing it the GPS data. So these are providing the GPS data, and then what data is Cygnus collecting itself exactly, and how is it using that GPS data? I know you talked about it a little bit. Could you clarify and dig into it a little bit?
Yeah, so there's several different ways that Cygnus uses the GPS data. I mean, the science way is it measures the strength of the signals scattered off the ocean surface as a function of position. That's how it gets its science. It also has a standard navigation mode. There's a small antenna on the top of Cygnus which measures direct signals from GPS, and it uses those for time synchronization, for geolocation, for precision orbit determination, and also for coherent synchronization of the GPS clock with the reflected signals timing, so that we can back out the Doppler shift of the signal.
Okay, thank you. Now we're waiting for questions to come in over the phone and online. And while we're doing that, actually, Chris, if you don't mind telling us a little bit more about some of the research motivations for this project. You talked a little bit about hurricane intensity being one of the key factors in this. And maybe you could just talk a little bit about why that's so important and where we are today and where we've been historically when it comes to hurricane track and intensity forecasts?
Sure. So there's a very careful, detailed record or accounting kept by the National Hurricane Center about the skill of their hurricane forecasts, and they've been doing this for many decades. And so they have records of the error, the statistical error in their forecasts for both the track of a hurricane, which is the location of the eye, and also the intensity of the hurricane, which is the maximum sustained wind in the hurricane, the Cat 1, Cat 2, Cat 3 thing. And if you look at those historical records for the hurricane track skill, the skill has been steadily improving year in and year out. And for example, over the last 20 years, we're about twice as good, or the errors are about half as big today as they were 20 years ago. So there's been steady improvement in hurricane track forecast skill. If you look at the record for their intensity forecast, there's been very, very little improvement in intensity forecast skill at all in the last 20 years. And the reason for that is that or one of the primary reasons for it is that the satellites today are just not able to measure what's going on in the inner core of the hurricane. This has been identified for many years as a primary lacking ingredient in the numerical forecasts that are used by the National Hurricane Center. They wish they had the information in the inner core of the storms, and they don't. And the exciting thing about Cygnus is it provides a new technology to both make the measurements in the rain and also to support the capability for many, many satellites in a constellation because of the inherent low cost of this particular remote sensing technique.
Okay, great. Thank you, Chris. Well, if we have no more questions, then I'd just like to, actually, I think we have one question coming in from social media. So, Emily, could you please read that question to us?
Sure. This one is from Chris Edwards on Twitter, and he's asking, do the microsats on Cygnus measure rainfall rates as well as wind speeds?
No. I mean, that's the great thing about measuring at such a long wavelength. We have negligible interaction with the rain. Actually, so we don't measure rain. We couldn't measure rain. We're not sensitive to rain. There's great value in knowing what the rain is in a hurricane because that monitors the conversion of latent heat back to sensible heat when the water vapor precipitates out. But what we plan on doing is there's a follow-on to the mission that I showed that picture of right at the beginning, the TRMM mission. The follow-on to it is the Global Precipitation Measurement Mission, GPM, which is up there now, and it has a constellation of instruments that can measure the precip, the rain rate, every 3 hours. And the intent is to match up those precip data products with the Cygnus data products and be able to constrain that air-sea interaction and nail the latent heat release.
Wonderful. Thank you. Any more questions from here in the audience, media members? Okay, if not, then I'd just like to thank everybody for taking the time to join us today and remind you once again that you can find out more about this exciting mission by going to www.nasa.gov/Cygnus. Thank you.